Okay, recording is starting.
Okay, good morning, everyone, and thank you all for joining us for this 2021 Student Symposium Continuing Education Seminar titled, Why Geology Matters. Before we get started, please let me share a few technical instructions with you. If you are having any technical problems, please visit Zoom support at support.zoom.us or type your question in the chat box. The recording of this seminar without permission from ASCE Texas section is strictly prohibited. All participants are muted throughout the duration of the seminar, and if you have any questions, please type them in the chat box in your control panel. Questions will be addressed at the end of the seminar. And now a quick message from our 2021 Student Symposium Advocate, CP&Y Incorporated.
Here at LCRA, we're committed to enhancing the quality of life of the Texans we serve through water.
Sorry about that, everybody. You got a sneak peek for the next video.
Okay, Lindsay, are we back to the introduction?
Thank you, Steve.
And now I'm pleased to introduce our presenter, Timothy Weston, who is the president and part owner of MLA Geotechnical, a locally owned geotechnical engineering and construction materials testing firm that has been practicing in Central Texas for more than 55 years. With a bachelor's degree from Virginia Tech and a master's degree from University of Texas at Austin, Mr. Weston has lived and worked in the Austin area since graduating and contributes 25 years of experience in geotechnical engineering and construction materials testing. Mr. Weston is currently the president of the ACEA and serves on the board of directors, the regulatory committee, and the symposium committee. In addition to his work with ACEA, Mr. Weston taught the local ASCE prep class in geotechnical engineering for the PE exam for many years. In his personal life, Tim coaches middle school volleyball at Brentwood Christian School, plays soccer, and serves on the board of directors of the Mainspring School. Tim and his wife Lori are involved in serving at their local church, working with Samaritan's Purse through Operation Christmas Child, and spending time with their children, Nick, Abby, and Jack. And now I present to you Mr. Timothy Weston.
All right, I'm going to share my screen here. Hopefully this is all going to go smoothly. Is everybody seeing the right stuff there?
Yes, Tim, we see your cover slide. Thank you.
Excellent. That means we're doing something right. Thanks for the introduction, Steve. We will jump right past the cover slide, so that's working. I'll give you, Steve gave you a little bit of background about me. I'll give you a little bit about our company really fast, just so you know where we're coming from and a little bit of bona fides about why we know some of this stuff we're going to talk about today. We've been a locally owned company here in Austin for 57 years. Austin's our headquarters, and we have San Antonio and Dallas offices. So you'll find out we're going to talk about the geology of Austin, San Antonio, and Dallas, not surprisingly. And then what we are is we're the regional experts. We tell our customers, hire the people with the local knowledge. We're them, right? We do geotechnical engineering, which means drilling sites and determining how to build things on them. I like to say everything from a bird bath to a high rise. And then weird way the industry is set up, we also do construction materials testing. So we do that drilling, we make some recommendations. A whole bunch of other smart people work on this project. Maybe it's building, and the civil engineer and the structural engineer do a bunch of work, and the architect and get a set of plans ready to build. And they hire a contractor goes to build it, and then we test while they build it. So we're there in the beginning, and then we're there as it's actively being built. So we'll test things like the soil and concrete and steel and all kinds of good stuff like that. The last thing we do to tie in with the last presenter was that we do forensic engineering on the geotechnical side. And so I have, like I was saying, if you were here in between sessions, I've actually testified live in court. I've given lots of depositions about when things go wrong. The reason we think that's important is it helps us make better recommendations on the front end. The next time we see a project like that, maybe we can make a better recommendation. Our focus today, you'll see, will be pavements and foundations, because that's what we do. And you'll find for us, what's really important is we have our own drilling fleet. So we've got 7 drill rigs, and where this is the one that I think gets numbers people like engineers. We've got about 120,000 borings in the ground in Central Texas in the last 10 years. So if you want to have drilled all these geologies to see what comes up, we're your folks. So without further ado, we'll jump right in. And let's see here. Yeah, here you go. So we get a lot of requests to do work on projects. And we like to say, you know, geotechnical investigation starts with sampling the earth, right? The first thing you do is you go out and you drill some holes. Well, for us, it's not. The first thing you do, and when I was fresh out of UT, I came here and they said, well, tell me what the geology is of this site. And I thought, really? Why in the world do we need to know that? But being, learning my job, I didn't question. I jumped in. I did a bunch of map studies by hand and figured out the geology of the site, right? So for today, I want you guys to think, I'm sure everyone's seen Geologic Sequence if you've ever been exposed to geology at all. What we'll be talking about today is Cretaceous age, and Eocene, right? I just like to think of it big picture wise, slightly younger than the dinosaurs. That's what we're going to be talking about most of our geologies today. We'll also talk about some recently deposited geologies. Think it could have been deposited yesterday, or it could have been deposited, I don't know, like 8,000 or 9,000 years ago. So that's recent in geologic time. Okay. First thing you'll learn about me is I like to teach in pictures, and I like to teach because I'm a visual learner, but 2, because I don't think you're going to walk away with much if I give you a bunch of bullet points on a slide, because you're not going to remember any of those, but you might, in your mind's eye, remember a picture, right? So this is one we'll probably come back to a couple of times. So this is Cretaceous geologic layers in Central Texas. So if I took my drill rig and came up here on top of the Taylor and I started drilling, and somehow my drill rig, which can only drill about 125 feet, could drill 2,000 feet, well, I could drill through the Taylor geology, the Austin, the Eagle Ford, the Butte, the Del Rio, the Georgetown, the Fredericksburg, and the Glen Rose. I could get them all, right? So think of it like a layered sandwich or a layered cake. As we start to look at some of these maps, you'll get an idea of why the map looks the way it looks if you can picture this layer cake. And just because it helps my brain and helps me learn visually, the big 4 geologies are the thicker ones. If you can imagine the topography changes in the region, the thicker geologies, Taylor, Austin, Fredericksburg, Glen Rose, are all hundreds of feet thick. And these other 4, Eagle Ford, Butte, Del Rio, Georgetown, they're relatively thin, 100 feet thick or less, typically in our area. And so you'll notice that Taylor, Austin, Edwards, Glen Rose, they cover most of the area, right? Okay, so keep that in your mind's eye as we move forward. Now, what did I have to figure out this geology when I started fresh out of school? Well, the Bureau of Economic Geology conveniently located, let's see, out my back door and on the Pickle Research Campus, they had gone and made a bunch of geologic maps, right? This is these orange that you see, that's the front pocket that holds a map that folds out. And here's the back page. This back page is interesting because it shows you the maps that are available. And you can see they've cordoned off the state into like 25 or 30 geologic maps. So you can say, great, I want to go get the one for my area, for Austin. And then you could get an idea of what geologies are in the area. Okay. So they did that with a bunch of graduate students. Okay. How did they do that? Well, it's interesting. Geologists and geotechnical engineers take a different approach. I go drill a hole and see what geology comes up. They're very non-destructive over in the geology world. So they actually pay graduate students hundreds and hundreds of pennies to walk around the state and find outcrops of geologies and find fossils and find indicator fossils for different geologies. So this is the kind of stuff they were looking for. And if we were all in a non-COVID situation, you would be holding these as we pass them around, but you're not, so you get to look at pictures of them, right? And so all of these different fossils, I've picked these up just by being at job sites. These are all on the ground surface. This is from the Austin Chalk. This is from the Glen Rose. We're going to talk about all these formations, right? These are from the Del Rio. And so, yeah, you can go around and pick up different fossils and figure out what geology you might be in. Okay, now, once I learned that, I thought, are you kidding? How could this possibly be this accurate, right? Like, seriously, people are just walking around and picking up shells. The amazing thing is we go and drill, and if my vice president was on this call, he would tell you that 99 times out of 100, when we look at this map and we plot we figure out where our site is and we go drill, that's the geology we find. So amazingly accurate. Okay, so what does one of these look like? Let's talk about that. So here is the Austin sheet. That's one of those 25 or 30 that covers the state. And so you're like, well, okay, well, how detailed is this? Let me orient you. This is town. Can you all see my cursor moving? Give me a thumbs up if you can, Steve. Yes? Okay, good. So this over here, that's Lake Travis. Austin is like this big. So not a lot of detail for Austin, right? Oh, College Station somewhere way over here. You know, and so this is a pretty, say, bird's eye view of the geology, right? So you know what keeps coming at a university? Can anybody guess? Students. So they have more grad students. So they said, okay, you know what? That's not a lot of detail of Austin. And Austin, a lot of people live there. A lot of things get built there. I would like more detail. So they went and did a specialty sheet. So now he said, just do me one that's super detailed about Austin. So now instead of Austin being really tiny and on the map, it's like, I don't know, the size of my fist if you had the map in your hand. So it's not a whole heck of a lot of detail. But now we've got Austin and you can start to see some detail. Here's Lake Travis, if you know the area. University of Texas is right in here, right? Here's downtown. Here's Town Lake or Lady Bird Lake flowing through downtown. Here's the airport, right? Here on the top here is Southern Round Rock. On the bottom of the edge of the map, you're in the north end of Buda. Okay, so you're now really got a good map of the region. And if we zoomed in on this, you've got individual streets. So I can figure out if I'm somewhere downtown at 6th and Lavaca or whatever, I can figure out exactly where that is, get an idea of what geology is there. So these became unbelievably helpful. Okay, now, the reason we talk about where they came from is so you can get an idea of, well, what does it represent? One thing it represents the geology at the ground surface, right? So you may, if you show up and you're drilling in the Eagle Ford, you may keep drilling and you may hit the Buda. If you show up and you're in the Del Rio, you may hit the Georgetown. Maybe you show up and you're drilling and you're in the Taylor, but you're at the bottom edge of the Taylor. You may only drill a few feet. Maybe it's 10 feet and you're in the Austin Chalk. Okay, so that's the reason that to understand the maps, where they came from, and understand that they are what's at the ground surface, and you might hit the next geology down if you're on a project. Okay, plowing forward into some of the details of each geology. First thing, before we do that, right? I like pictures and I like rules of thumb. Rules of thumb because you can walk away and remember them, right? So if you're on the Austin Metro sheet, which we will focus on today because it's easy, we're in Austin and we've got it We've got it right here. We're going to come back to this several times. Okay. Rules of thumb, green equals rock. I know that's very technical. There's a bunch of like calculus involved to remember this. Green equals rock. So there you go. I think we can remember that for the rest of the presentation. And purple equals clay. Okay, now we're getting somewhere. We got rock, we got clay. Last but not least, orange or yellow, they're kind of orangish yellow, right? Equals question marks. Now, as an engineer, you might say, well, question marks, that's not actually useful. Well, no, it actually is useful. That means you could get a little bit of everything, right? So you got to expect variability. You got to expect that you could get sand, you could get gravel, you could get clay. Okay, so bear the colors in mind: green rock, purple clay, orange and yellow, question marks. This right here is just a piece of the larger Austin sheet we were looking at. Right now we're looking at downtown. Here's Longhorn Dam. Here's where everyone is canoeing and paddleboarding right here on Town Lake. All right, South Austin, the airport's off to the right. So you can see just in downtown and South Austin, look at all these colors. You could literally have one geology on one side of the street and another on the other side of the street with completely different characteristics. Okay, those are faults and geologic contacts, meaning faults not in the sense of seismic faults. Don't think California. Think if you've taken a geology class, just think that one geology has been pushed up next to the other and they don't belong next to each other. And so that's how they're pretty sure there's a fault there. If you get a geology that should be 1,000 feet away in the sandwich that we showed earlier, right next to another geology, pretty sure we've got a fault going on there. Okay, now let's talk about some of our geologies, and I already previewed it probably too fast, but the one geology, if you live in this area that everyone talks about, right? If everyone was unmuted, I'd say, what was it? And invariably, the audience can come up with the answer, even if they know nothing about geology, because we talk about the Edwards Aquifer all the time. Talk about it on the news. Talk about that particular limestone formation for various reasons. Okay, well, let's talk about that one first. Okay, the Edwards limestone. The Edwards limestone is rock geology, covers a large piece of our area. Let's see, we're going to go to Austin Metro sheet. Okay, so on the Metro sheet, the Edwards is the darker green here. You can see it runs from West Buda, it runs up through Southwest Austin, it runs through Terrytown, it runs up, it's running up here. This is essentially Mopac going through here. So it's west of Mopac. You can see it heading over to Lake Travis, and it widens up. You're roughly at the Williamson County line at the top of this map. If we went and got the next map, it's going to cover a large portion of Williamson County. It's going to cover the Texas Crushed Stone Quarry. That's in the Edwards limestone. And so you've got a lot of people living in the Edwards, a lot of things being built on the Edwards, and it will go all the way south down into San Antonio. So you can be on the Edwards down there, and it will continue heading north and peters out between here and Dallas. So I don't do a lot of, there is no Edwards limestone drilling in the Dallas-Fort Worth area, not in the Metroplex. Okay, so what is the Edwards like? Several things. One, you hear about it as an aquifer. So that means one thing to me always. If it's an aquifer, it holds water, and it's a limestone, so it must have some holes in it, right? So yeah, here's a sample of an Edwards limestone. So that's a core sample. And then, I know people picture a core that we go out and drill a core, that it's this smooth thing, like it's a stick of marble. Well, sometimes it is, but not in the Edwards limestone. It usually has holes like this in it. It'll have pockets of clay in it. Sometimes the holes get really big. What do we call those? Yeah, we call those karst. That's a fancy word for cave, but my environmental geologist friends don't like me to use the word cave because that means a specific thing in environmental geology. So it's a karst feature, but that means sometimes you can stand inside of it. If you've been to inner space caverns, the highway department learned about inner space caverns drilling some piers for a bridge for I-35, and you'll notice the I-35 is no longer over top of inner space caverns, but happens to be right next door. Also, for you students that don't get that far from campus, if you go to the University of Texas, you should go up there, wait until about August 15th when it's 105 outside, because it's like 68 degrees inside the cave. Okay, now what can we learn from a geotechnical perspective about, what can we learn about that? How are we going to apply that to our geotech project? Well, we can apply several things. One is when we've got those holes in the limestone at the ground surface, what happens? One, they fill up with clay. So you might have, if this is a 6-foot cross section, you might see pockets of clay on your job like this. Sometimes the pockets of clay are 15 and 20 feet deep, right? So imagine I am drilling holes for pier design on a job in this limestone, and I'm going to drill every pretty large building. I'm going to drill, say, 100 foot on center. Well, I might entirely miss one of those pockets of clay. I might hit one and design for it. And it turns out it's no larger in diameter than 10 feet, or maybe it's half the job site. So things that we can learn is, number one, variable conditions are likely to be encountered during construction. Number two, we might want to increase our scope on the geotech side and drill some more holes to get a little bit more information because we're expecting variability, right? And so those are the kinds of things we can think through. And we'll talk a little bit further on the back end of this presentation about karst features. Okay, so next geology, let's go back to the Austin sheet. So let's think, this was the Edwards, this darker green. If we go west, we get the Glen limestone. That one's easy to picture, and that's the easiest geology to see in the whole region. Go to the hill country, look at anywhere there's a cut in the limestone, you're looking at the Glen most of the time. Okay, so the Glen limestone, easy to see. Go over to the bridge, the famous Austin Bridge. It's actually, if you don't know, it's called the Pennybacker Bridge. It's on Loop 360, right? Which isn't a loop, just in case you're new to the area, right? This is easy to see. Here's the Glen Formation. Here's a giant cut with a highway through it. What can we learn about the Glen just from this picture? Pretty easy. We can learn, number one, it's pretty massive. It's pretty intact. You don't see the big variability with pockets of clay like the Edwards, which makes it possible for this to stand vertically. The other thing we can see in this picture is just above this car here, you can see an area that looks kind of weathered. That's because the Glen is a sandwich of hard limestone and soft limestone and hard limestone. And by soft, I mean like dig it out with a backhoe soft. And by hard, I mean get out the jackhammer and the hoe ram it out. And so you can expect these layers, okay? And you can learn things about them, about the Glen from that. Normally, when we make a cut in the Glen like this, we get water seeping out of it. You're surely getting water seeping out probably right in here. Notice things growing out of the weathered limestone. Well, we need water for that, okay? So if you're on a project in the Glen you can, and you're thinking like a geotechnical engineer before you go out and sample, I might want to think groundwater, especially if we're going to have a cut. I may just have a natural occurring on a hillside where this layer reaches the ground, and the water tends to travel in that layer. So maybe I have what we would call in the hill country a spring, right? There's this town near us, right, that we've done a lot of projects in recently in the last decade. And we go out there and we're working on a project and someone says, I can't believe it, we hit groundwater. To which we say, you do know the name of the town is Dripping Springs, right? Springs is actually in the name. Okay, well, this is the geology that's causing the springs. Water rains, it's absorbed into this limestone. It's super hard for it to travel in this limestone. It's got to travel through cracks and fissures, but when it hits this weathered layer, this is more like it'll act more like a clay, and the water will travel horizontally. And it'll travel horizontally until it comes out of the ground, and lo and behold, you have a spring. And sometimes the spring, if it's a rainy season, it rains up, it's wet all the time. And then if you're in a dry season where it hadn't rained for months, it might be completely dry. So to test this theory, go out here, right, and check out this cut about 2 weeks after it's rained for 2 or 3 days, and you'll see water still seeping out of this cut. Then go out there in August when it hasn't rained for a month and it's bone dry. Okay, so it's an intermittent type of groundwater, not a groundwater table like you might have in, say, Houston. Okay, to get a look at the Glen rows, whoops, going backwards. So you can see the Glen row is very different than the Edwards. You can see no obvious holes. It's relatively intact, and this is pretty typical of what we would core through. Okay, let's go back and talk about the last of the big three for coverage of our area is one called the Austin Chalk, surprisingly named after Austin, Texas, right? Let's take a look at where it's located. Austin Chalk really starts south of Austin in Buda, and it's the chocolate chip mint ice cream color. It goes right up through downtown, all those giant buildings that are being built downtown. They're all anchored in the Austin Chalk over some flood deposits from the Colorado River. Most of the buildings, in fact, every building at the University of Texas is on the Austin Chalk. We are right in here at UT. So you can see we've got, we'll talk about the red, but mainly we've got the mint green color. This geology goes all the way up from Austin, up I-35, all the way up through the Dallas-Fort Worth area. So lots of structures built on this chalk, Austin Chalk geology. And there's some really great things about it. Let's show you a picture of it real quick. Okay, so this is the weathered, what they call the weathered portion of the Austin Chalk. So it's going to be the stuff that you first drill through. And then beneath it, it turns to this gray color. And great things about the Austin Chalk. It's very consistent. So when you find it, you tend to find it. You tend to stay in it. It's intact. So if you hit water, it's on top of it. You don't drill through it and find water down in it. It's not an aquifer. It would be considered an aquiclude, which is a fancy word for doesn't let water in, right? And so if you find water, it's on top of the Austin Chalk. And it's relatively hard. And so you get in the weathered stuff, the stuff you first drill through, and it's hard. And you've got some pretty good capacity for piers or for footings. But if you need more capacity, you can generally keep drilling and get into this gray stuff. And this stuff is unbelievably hard. Locally, they call this that there blue rock. Yeah, I know it's not blue, it's gray, but that's what the contractors call it, that there blue rock. Yeah, the blue rock is the stuff that breaks their equipment. And so what can we learn about from drilling through this in a geotechnical report? If you run into this light gray stuff and you're in the Austin Chalk and you're consulting with the contractor, you might let them know this is the breaks your equipment rock. So here's some information. Bear this in mind. Don't tell the owner when it's time to go do this project that he needs a change order because the rock is too hard. That kind of thing. Okay, last but not least on the rock geologies. Of the ones we're going to talk about, the Buda limestone. Okay, look, it's thin. See that? Approximately 45 feet thick, but it can be deceptive, and here's why. Let's go look at this map. So the Buda's light blue. See, it's in tiny little areas, not in doesn't cover much, right? So why would we care that much about it? Well, the reason that we care is that the Buda, going all the way back. Whoops, sorry. The Buda is very thin, and it's between two geologies we're about to talk about, the Eagle Ford and the Del Rio, that are unbelievably expansive clays. And so the reason that the Buda is important is there's nothing too exciting about it. It's a hard limestone, 45 feet thick. The problem is if you blow it and think you're in the Buda, but you happen to be in the Del Rio, your project will fall apart. And by fall apart, I mean, it might fall down. And we're going to show you some of those here as we progress. So the Buda is important in that if you blow it and you're actually in the Eagle Ford or the Del Rio, you're in big trouble. You've got the polar opposite recommendations than what you need from a geotech standpoint. Okay, let's move on to some, there we go. Yeah, here we go. All right, so let's talk about expansive clay geologies. First thing is, what's expansive clay? Now, depends upon your university and how much they care about expansive clay. I'll pick on my university for a minute because, well, we're hosting this place. we're hosting this shindig, and I happen to go to school there. And when I was in graduate school there, the amount of time we talked about expansive clay was 1 hour, not one class hour, 1 hour on the clock, not 1 credit hour, 1 total hour, 60 minutes. Okay. Now that has changed massively at the University of Texas. I know several of the professors that are doing great research there and specifically into expansive clay. And so that's good to see, because that is what I'm dealing with as the geotechnical problem of the region all day long. Okay. So it's an important thing regionally. The reason that it doesn't get dealt with more, and especially if you leave the region, is that this is an expansive clay, discussion, but you got to understand this, is that it's a regional thing without simplifying too much. But if you're really not in sort of like Texas, Louisiana, Colorado, California in the United States, you probably never even heard of this. And then internationally, there's only a few places as well. So most people don't deal with this, don't know about this. It's very local knowledge stuff. Okay. But expansive clay is the simplest thing of all. You add water to it, it swells. It might swell 6 inches, 8 inches, 10 inches if it's very expansive or more. And then when it dries out, it shrinks. It cracks and it shrinks. Very simple. We're going to talk about the expansive, the 3 main ones for Central Texas, and then a 4th one that's in San Antonio. Okay, first is worst, right? First is something called the Del Rio clay. I want to first off show you where it is. Oops, I think I added one of these slides. There we go. Normally I have a map up that you're looking at, but I got to flip back and forth to the map for you guys. So the Del Rio clay is this darker purple. Remember, purple is clay, right? So it's not in a whole lot of areas. And if you remember from our sandwich, it's underneath the butyl limestone. So the Del Rio clay is here in the dark purple, and it's running a band that's roughly following on this map Mopac, right? On either side of it. Okay, so what's tricky about the Del Rio clay? Well, in geotechnical engineering, the plasticity index from the Atterberg limits test has been correlated to expansiveness. And people don't necessarily run the swell test all the time. They just run a PI, run the Atterberg limits, get the PI and say, oh, it's 45, it's expansive. It's 62, it's expansive, or it's 12, it's not very expansive. Okay. Well, the Del Rio is one where unfortunately that correlation does not hold. Okay. You get PIs that might be 25 to 35, which around here would be sort of moderately expansive, only it's unbelievably expansive. Okay. So number one, it tricks the engineer. It can trick the engineer because the lab results that are typical are faking you out. Next thing that really fakes people out is, whoops, right here. This is a sample of the Del Rio, and if I pass it around, you wouldn't believe it. It's hard as a rock, as in when you're excavating it and it's dry, it's hard like a rock. So the contractor is also fooled. It's light colored, so it looks like a weathered limestone, right? And it's hard. So the contractor thinks, okay, no problem. I'm in rock, only this is the most expansive clay of the region. Yikes, right? And while we're here, this is Eagle Ford, geologic designation KEF. Similar problem. It's really, really hard. It's also light colored, also gets mistaken for limestone. So the Eagle Ford and the Del Rio have that same problem. Okay. So you get those things that fool you in those locations. You get the same problem with the PIs in the Eagle Ford. Okay. The reason I put the Eagle Ford separately and don't talk about them specifically, don't talk about them together because they're very similar, right? Del Rio and Eagle Ford, is that in Dallas, the Eagle Ford, instead of covering a small area, right, back to coverage area, it's the lighter purple. Again, not covering too much of Austin, but in some key places where there's construction, downtown, Round Rock area, up along Mopac, right? Doesn't cover a whole lot of our area, but in the Dallas-Fort Worth area, it opens up, widens up, covers a wide swath of Dallas area. And you might hear Las Colinas got the most expansive soils around. And man, it does. Unbelievably expansive. We have it here in Central Texas too. It's just not so widespread that it's been dealt with as often. Okay. So Eagle Ford, Del Rio. The next one that is the big actor, the Taylor clay. It's very expansive. And the best I can say about it is it makes a great pond liner. The great thing about the Taylor is it doesn't lie to you as a geotech, so you know what you're going to get. You run a plasticity index test, you get 55, and you go, oh boy, very expansive. What am I going to do? Instead of in the Del Rio, if you're new and you're inexperienced geotech, you might think this isn't so bad. All right, so at least you're not being faked out. But unfortunately, it's the lavender and light purple. It's all of this. Okay, so if you're familiar with 130, right? And here's the airport. 130 is out here. All of this new development that's going along the 130 corridor, all in the Taylor clay. We used to really not build a whole lot out there. Well, now we do. It's actually the city of Austin's it covers most of the city of Austin's desired development zone where they have incentives for development. And it's where the airport is, the Formula One track. It's Tesla isn't built on it, but the new Tesla plant is very close to it. Okay. And so we're going to be building things on this. So if you're going to go out, if you're going to be working in the Austin area, you got to be familiar with this one. Now you think, okay, well, how widespread is it? Well, east of I-35, it goes all the way to Dallas and it goes all the way to San Antonio. So it is widespread. We build on it all the time, and we've got to be careful when we're building on it. We have to know what we're building on. Okay, that's our major actors on expansive clay in the region. I want to go talk to you guys just about a couple of expansive clay things to like. What do you need? What should you watch for? Things that are weird that aren't in your textbook is really what we're talking about. One of them is downhill creep. Now look at that. There's reading. Oh my gosh, you don't have to read it. I'll read it for you. All right. If you find a site that's one of these expansive clay sites, if it's too steep, 5 to 10%. Now my civil engineering friends don't think of that as steep, but I will tell you that in expansive clay, that's very steep. Okay. It says your site may be unsuitable for building. Uh-oh. That's not what you want to read. Okay. So here's what happens. Imagine you come up, you get an expansive clay site and it rains. What does the ground do? It goes up, right? And then we get a drought, dries out. So the ground goes up and down like this. Well, if you introduce a slope to it, right? I get swell up like this. Well, for some reason, when it shrinks back down, it doesn't go here. It goes, oh, is it really going to do that to me? It's not going to even show it to me. All right. So what happens is this particle comes straight down. And what ends up happening is the particle, if you're just to like somehow instrument a single particle, it slowly moves down the slope. Not in the slope stability failure. Think in the magnitude of inches per year. But those inches per year, I always thought coming out of school, like, well, I'll just build something out of concrete and steel that's stronger than that soil, and it'll overcome all those forces. It won't. We've torn down buildings because the downhill creep has moved the building so much. The next thing you do is, if the building was sitting on the ground, so people say, well, why don't I use piers? You know what it does to the piers? Makes them lean over. Still an unhappy building when the piers are leaning over. That's not really what you want out of your pier. And so this is a real problem. You can stop this. I mean, the forces aren't insurmountable, but the problem is you need a public works budget to do it. You need serious piers, a serious set of piers that's in no one's budget when you're working on one of these projects and you're trying to build up, say it's a warehouse building or something, right? So this is one to be very careful with, okay? Just be aware of. Okay, other expansive clay things to watch for. Lateral earth pressures in expansive clay, right? And if you took the geotech class, which if you're a civil engineer, you certainly have or you're about to, right? Lateral earth pressures sounds like a fancy word, fancy thing, but it's really if I have the weight of some soil and I cut it and I build a retaining wall like we have here in this picture, how much does the weight of the soil push laterally on the back of this wall? Okay. Well, in expansive clays, the problem is that can be greater than the unit weight of the clay, which is like, say, double what some other soils might be. Okay. And there are a couple of examples, which we're going to get to. One we call the Castle, which you can go visit here in Austin. It's at 11th and Baylor. And the other is River Mist in San Antonio, where people got the lateral earth pressures wrong and their wall either fell down or it cracked so bad they abandoned the project. Okay. So let's plow into those. We're going to skip this. How much time do we have, Steve?
Looks like you got 20 more minutes.
Oh, okay, good. Good.
Actually, Tim,
10?
more like 10, yes.
Okay. Oh, no, 10 is good. That's where I thought we were. Perfect. We're going to skip that because we already talked about it. Yep. I want to go talk about the mixed geologies. So you remember back?
I was busy taking notes on your presentation, Tim.
Man, I don't know about all that. So remember our map, right? One thing we didn't talk about is these yellowish orange, yellow and orange geologies. You'll notice they're all along rivers and creeks because they are flood deposits. Okay, so they're alluvium. And so some of these deposits could be very recent if we had a recent flood, and some of them are older. If you know the history of Austin, we used to flood up to roughly like the Capitol before we put Tom Miller Dam in place. And then you'll notice, you'll see flood deposits right here, right up to about 11th Street in front of the Capitol, because that's where it used to flood, right? And as you get down out of the hill country and you get in a flatter geology, you can see what these floods did. You can see wider spread. And you can see some older geologic floods in the orange, okay? Well, what to know about those is, right, they can be clay, sand, or gravel. Just depends upon the speed of the flood as it receded. It depends upon the parent geology that was eroding upstream, right? But you can know that you could get a little bit of everything, a little bit of clay, a little bit of sand, a little bit of gravel. Often you'll hit a water-bearing layer if you drill deep enough. Often you'll hit a layer of gravel or sand that will bear water if you're in a bunch of clay. Right, so those are important things, right, to know. Even if you know that it's variable, that is a piece of information. Okay, want to do a few case studies real quick, just because those are a little bit more interesting for everybody, and there's more pictures. Okay, so here's a case study in Lakeway, and I can talk about it because it was on the cover of the Lakeway newspaper. Not really a very big newspaper, but still in the newspaper. Not how you want to be in the newspaper. This was my project. This wall was inspected by us, not designed by us, and it came out, and the wall is gone here. Not supposed to be gone. Okay, this is a geogrid retaining wall with what they call butter blocks. So 6 foot by 2 foot by 2 foot blocks of limestone, and there's geogrid going back in here. You can almost see the geogrid layers in the slide, right? And this wall fell down overnight, right? So what happened is we're in Lakeway, we're in the Glen limestone, and so we're getting water seepage back behind here, and you'll notice the gravel and the geogrid stayed in place, but the what we call the butter blocks, the limestone at the face, it all fell off. So we didn't know what happened. We went back through our records. Lo and behold, we didn't get called out until the footings were done. And so the contractor had assumed that the footings were in limestone. Remember, I showed you the Glen has soft layers and hard layers. Well, if you saturate the soft layer, it essentially turns to the consistency of butter. Well, they thought they were actually setting the footing in limestone, but they had set it in that soft layer. Then they got all that water that was collected at the back of this retaining wall, and they didn't move it out fast enough, and it saturated that stuff the footing was sitting on, turned to butter, and they essentially had a bearing capacity failure right at the bottom of this wall, and all the blocks sank into the earth and then fell over face down, and they're all out in here. Fortunately, you can see the streets are in. They were about to start construction of condominiums where people might have been in their backyard. Thank God they were not. But we went back, excavated down, figured out they were in that soft limestone. And my lessons from this are, don't underestimate how much groundwater the Glen can make, because it can make a lot. And you should get inspection on your footings, right? Because once again, the contractor got fooled simply by the color and should have had a professional out there doing the inspection instead of doing their own inspection, right? So That one, fortunately, we fixed. There were thousands of linear feet of wall. Just to recap this thing, the owner rightly said to me, "Oh my gosh, I'm worried about the other walls." Fortunately, the other walls, except for this one, were all sitting in limestone. So they were safe because we went back and dug test pits and exposed the front edge of the footing on all of those. I think, I want to say 50-foot intervals. This one cost the contractor $1 million. It all had to come down. They had to carry the loads down to limestone and rebuild this wall. And you can see this is a large piece of equipment. This was like 16 feet tall. Okay, some more walls. This was on the cover of a slightly larger newspaper you might have heard of, the San Antonio Express News. This is the River Mist subdivision. You see this wall here? It's cracked. It's as tall as this 2-story house. Not really what you want. That's not the scary picture though. This is the scary picture. This is the crack on at the back of the uphill house. Think those people were nervous? Yeah, they were nervous, right? So I evacuated all those houses, started a case study, how do we fix this? Got in there, and some great folks, the Keller Engineering folks who I think might be presenting to you guys today, or maybe in another symposium that I was looking at. But they got in there, did a design, build, fix this thing. But there was also why did this happen? Okay, here's why it happened. This wall was designed to hold up the lateral earth pressures of limestone, which, by the way, if it's the butyl limestone, are 0. You only have to hold up whatever backfill you put behind the wall because the limestone's not pushing on the back of the wall. The wall was designed from a pavement design report with a boring that was up here between these houses. They'd only drilled a couple feet into limestone. Remember, we showed you that sandwich earlier. We won't scroll back to it, but that was the butyl limestone. This right here is the Del Rio clay. All they had was a few feet of limestone over clay. They should have been designing for clay, but they didn't actually have borings deep enough. So there's a few things going on here. The geology was misdiagnosed, if you will, but not really. Somebody designed a wall from a pavement report that didn't talk about walls that looked like there was limestone everywhere. And it turned out there wasn't. And so it's a misdiagnosis, misuse of geotech report, but geology played a part in that. People saw that they were in limestone and just assumed, well, we'll stay in limestone, right? Sometimes yes, sometimes no. So that's a interesting one. This one I like because I get calls on this still, and someone's about to develop this. So if anyone on this call is involved with it, I hope the best for you. So this is Austin's Graffiti Park. If you're an artist, you should go and do some graffiti. I'm not. I can only draw straight lines. I'm an engineer, so I've never done that. But we have a graffiti park. Anybody think that the developer was intending to have Austin have a graffiti park when they went to build these condos? Right, they did not. Okay, so what happened is, this is a large cut in the Del Rio clay. It's experiencing two things. It's experiencing downhill creep. It's experiencing really high lateral earth pressures. So they stair-stepped down this cut, and you can see how you can kind of envision how they were going to do these structures. And then they had some open elevator pits. The first time I was ever here, this wasn't a graffiti park, right? This was 22 years ago or so. And they got this far in the project. The elevator pits were no longer vertical. The walls here, you could reach your arm through the wall, your arm, that's how big the crack was, not a good sign, and touch the soil behind because it was moving from overloaded lateral earth pressures. And the entire hillside is experiencing downhill creep. If you know our area, this is at 10th and Baylor, so this is a block west of Lamar at 10th Street. And so essentially, Baylor Street is moving towards Lamar in inches per year, no joke. So go there, check this out. If you stand right in front of this, you can look up, you can look north, and you can see these little retaining walls that are holding people's yards up, and the retaining walls are leaning out over the sidewalk. That's downhill creep, okay? And
1 minute, Tim.
Yep, perfect. And across the street, we built some condos. And what I did was I was involved in that. I had them isolate the whole system from the downhill creep. Okay, last thing, and then to question and answers. So we also, in this area, we run into a lot of karst. Why? And when? Generally, we run into it when we're trenching for utilities. You can see this wastewater lines going in. We got this opening. I get the call. We found a cave. It's usually not a big deal. It's not really a cave. It's something really small. This was not. This is north of San Antonio. Here is a structural engineer right here. Here's one of my colleagues. You can see this. You could stand in there. The ceiling was probably 25 feet high. It was the size of a football field inside there. And a quick story, and then we'll go to Q&A. So we were here tasked with how do we get this utility line in? And so we were there to assess how hard the rock was. The rock was very hard. The structural engineer had a great idea. We're going to take an I-beam. We're going to turn it on its side right in here. We're going to use it to bridge across here. Then we're going to fill this in with concrete. And then we're going to encase the line in concrete in case it leaks. And we're essentially rebuilding the roof of the cave. We keep the integrity of the cave. We keep groundwater safe because the cave is filter for our groundwater. And we get to have this utility line and the streets and the houses above it. The rock is all fine. We can build all of that. And so we get the TCEQ involved. They like our solution. They sign off on it. And you think, all right, we're going to build it. But instead, some people from the neighborhood somehow found out about this cave. The contractor had it surrounded by fence, but they did not have a 24-hour security guard. So these people snuck in at night, took pictures, sent it to the newspaper, and the answer from the TCEQ changed overnight. They said, your solution is great. We still want you to do that to close the roof of the cave, but no sewer line, no road, no lots. Get rid of all of that. All political, not engineering. So we learned a few lessons there. Number one, we can rebuild the roof of the cave. Go out there. You need to understand, what geology you're in, how hard the rock is, all that good stuff. And the contractor learned a lesson: 24-hour security when you find something like this would be a good idea. Okay, that's it for me. Thanks for listening to the ramblings of a 50-year-old geotechnical nerd.
Thanks, Tim. So we have one question here from Sean Merrill, and he's asking, can you talk more about caves being discovered during or after construction?
Yeah. The news, actually, the last time one was discovered, had me go on and talk about this very topic, which was funny because my mother is still afraid of caves because she lives on the Edwards. So she doesn't trust me. So I'm not sure that the public would trust me either. But the hard thing is that they're very hard to discover. And when we'll do things like, say we're doing a building with piers, we'll recommend pilot holes. Normally things are moving so dang fast, no one drills a pilot hole to check out for things like this, because the geotechnical investigation is really just not enough, right? And so what ends up happening is it all ends up being problem solving during construction. So hopefully you don't find something big and it's something relatively small. But I was in one yesterday. It was hit in a utility line in Round Rock, and I was out there with the environmental geologist. It was definitely a feature that was part of the groundwater filtering for the area. So we're tasked with two things. We need to allow the feature to continue as a filter for groundwater, and we need to make sure there's structural integrity for, in this case, the road that was going to be above it. And so I worked out a solution with the environmental geologist that involved some concrete, some gravel to allow water to continue to flow through the feature. And it's really a case-by-case thing. So I don't know how much that answered your question, but it really, in our region, it happens while things are under construction, and you need to have a good environmental geologist that that can come out quickly, and then someone like me that if it's a bigger problem can help with capacity and things and work together with the environmental geologist.
Thanks, Tim. I think I can speak for everyone when I say that presentation was fabulous and really opened our eyes to why geology matters. There's a lot of stuff there. It was like drinking water from a fire hydrant, and Lindsay has told us where we can go to find more information on the geology of Texas. So thanks again, Tim. Look forward to hearing from you again in the future sometime. And I think that concludes this session. And now I'll turn it back over to Lindsay.
All right. Thanks for having me, guys.
Thanks,
Thanks,
you.
Tim.
The recording will now end.